In part 2, we will discuss three popular relations. The first one is the empty relation. For example, consider this relation R given by the ordered pairs x, y such that x, y belongs to the set A, where the definition is x square plus y square is lesser than 0. The given set A is, suppose 1, 2, 3 up to 9. Consider the given definition. It says the sum of the squares of the elements in the ordered pair is lesser than 0. Since for any real number x square, y square both are greater than 0, that means x square plus y square, the sum is always going to be greater than or equal to 0. So it's not possible to have x square plus y square less than 0 when we are considering x and y as an element of this set. If we even consider the x and y as real numbers, then also it is not possible. Only in case of imaginary numbers it is possible. So according to the given definition, there is no such ordered pair that will satisfy the definition of the relation R. That means the relation is a null set or void set, and we will call this empty relation. Second popular relation is universal relation. Suppose A is a set that is representing the natural number set. So consider a set of natural numbers, that is n, and a relation R is defined on n to n. That means the domain of the relation is set n. At the same time, the codomain or the range of the relation is n also. The relation is given as and is defined by mod of x minus y is greater than 0. Now just look at the definition. Whatever be there within the mod, whatever be the value of x and y, whatever be the operation plus or minus or multiplication or division, the final outcome of the mod of x minus y is always going to be greater than 0. It doesn't depend on the values of x and y. So whatever be the source set or the domain and whatever be the codomain, this relation or this definition is going to be satisfied by all. That means R is equal to n cross n. That means all the elements of the power set n cross n will satisfy the relation. That means R here, according to the given definition, represents universal relation. Third or the last popular relation is identity relation. Identity relation simply means that the element is related to itself only. For example, consider this definition of R x, y such that x, y belongs to the set A defined by x is equals to y. So in this case, whatever be the set A, this for example 1, 2, A, B, the elements of the relation will be 1, 1, 2, 2, A, and B, B. That means the element is related to itself only. 2 is related to 2, A is related to A, B is related to B. This kind of relations are called identity relations. In part 3, we are going to discuss types of relation. This is the most important part of this whole subunit. You are going to face most of the questions from this part 3. So first type of relation is the reflexive relations. Suppose we are defining a relation on set A, and if for all A belongs to the domain set, A is related to itself, or A comma A is an element of the relation R, then we can call that the given relation R is reflexive. Second one is symmetric. Consider the same relation A to A, and here we need two elements from the domain. If A comma B belongs to the relation, or A is related to B, then B is also related to A. That means B comma A also belongs to R. If this is true, then the given relation is symmetric. The third one is transitive relations. In this case, we need to consider three elements of the domain, and the condition is that if A comma B belongs to R, B comma C belongs to R, then to make the relation transitive, A comma C must belong to the same relation. Let us discuss all these three types of relations with simple examples. Suppose we are defining a relation such that n to n are natural numbers. The definition of the relation is given as x comma y such that xy belongs to n, and defined by x is lesser than or equals to y. Now we are going to check, is this relation reflexive, symmetric and transitive or not. So first one, reflexive. For this we need to consider an element, let A belongs to n. Now can we say that A is lesser than or equals to A? Yes, because A is equal to A. That means according to the given definition of the relation R, A is always related to A, whatever be the value of A from the set n. 1, 1, 2, 2, 3, 3, all these kind of elements are going to be a part of the relation. There will be no such value of A for which A comma A is not a part of the relation. That is why the given relation defined by x lesser than or equals to y is reflexive in nature. Now the second type, is this relation symmetric? For that we need to consider two elements from the set n or the domain n. If A is lesser than or equals to B, for example, A is lesser than or equals to B, then B is not lesser than or equals to A. It is not possible. For example, 1 is less than 2, then we can't say that 2 is lesser than 1. That means if A comma B belongs to the relation, or A comma B satisfies the relation, then B comma A doesn't belong to the relation or doesn't satisfy the relation. That means the given relation is not symmetric. Is this same relation transitive? To check that, we need to consider three elements. For example, A, B and C are the three elements from the domain of this relation, such that A related to B and B related to C. That means A lesser than or equals to B and B is lesser than or equals to C. Then for sure we can say that A is lesser than or equals to C. Let us discuss this with an example. Suppose 1 is lesser than or equals to 2, 2 is lesser than or equals to 3, then for sure we can write that 1 is lesser than or equals to 3. That is, if A comma B, B comma C belongs to R or satisfies the relation, then A comma C also belongs to the relation. That means transitive. The last part of the theoretical discussions about relation. In this part we will discuss the equivalence relation. A relation is going to be called equivalence relation if and only if satisfies all the three types of relations. That means it has to be reflexive, symmetric and transitive at the same time. Only then it will be called equivalence relation. For example, suppose a set A, it contains all the straight lines in a plane. In a particular plane there can be an infinite number of straight lines, so the number of elements for this particular set is infinite. Now the relation A to A is defined by this both ended arrow represents defined as or defined by. So this relation A to A is defined by is perpendicular to. This is the definition. And obviously the domain is set A and the codomain is also set A. So we are going to pick any two lines from this set A. Then we are going to check are they perpendicular. If yes, then they are going to be a part of the relation or element of the relation. If not, they are not going to be a relation. Is this relation equivalence relation? To check that, we need to check is it reflexive, symmetric or transitive. So to make it reflexive, can we say that AB, a straight line, is perpendicular to AB? Is it possible that any particular line is perpendicular to itself? It's not possible. That is not reflexive. Now, if we say that AB, any particular line from the set A is perpendicular to PQ, another line from set A, then we can also say that PQ is perpendicular to AB. So if AB comma PQ belongs to R, then PQ comma AB will also belong to the given relation. That means the given relation is symmetric. Now the third condition, is it transitive? For that we need to consider three straight lines. Suppose this is the straight line AB, this is the straight line PQ, and we are considering the third straight line MN. So in this case we can say that AB is perpendicular to PQ and PQ is perpendicular to MN. But we can't say that AB is perpendicular to MN because AB and MN are parallel in nature. It is clear in the diagram. So even though AB and PQ are related, PQ and MN are related, but AB is not related to MN. So the given relation is not transitive. Since the given relation is not satisfying all the three types of relations, so we can't call this an equivalence relation.